Hello, everyone. My name is Adam Zahir. I'm a PhD student from Universidad Carlos III in Madrid. And today I'm going to present the real-time digital twins demo. So this work has been developed in the context of the D6G European project, and it includes the collaboration of several partners from the project, in particular UC3M, UBA, ELTE, and Nubis. I will start with the definition of a digital twin. So basically, a digital twin consists of a virtual representation of a physical object where the connection between both of them is done through this interconnected data, and it provides simulation for real-time prediction, optimization, monitoring, control, and improved decision-making regarding the physical object. Based on their functionality, the digital twins can be classified into three types that are monitoring. So here, we only have one direction from the physical object to the virtual model, providing some monitoring info. Then the second type is simulation. So in this case, we also have the control from the physical object to the virtual model. So we are updating the virtual model and providing and performing some kind of simulation in order to predict the behavior of the physical object. And the last one is operational, that enables to interact in real time with the virtual model, and based on these interactions to send the control commands to the physical object. In this demo, we'll focus on the operational digital twin, which is the most complex one. What I previously described is the digital twin application, but in this demo, we'll focus on the complete digital twin system. So a digital twin system not just includes the digital twin application, but also the networks that interconnect the physical object with the virtual model, and also the computing infrastructure. Then for the radio access part, we have different type of wireless communications. So we can have device to infrastructure or device to device communications. Based on this, in this demo, we'll have a complete digital twin system that is distributed across the device, the edge, and the cloud, where the robots are remotely controlled and they operate using algorithms that are executed at the edge. So the robots will continuously send sensor data in upstream to update the virtual models, and while also receiving control commands in downstream. So the main challenge here will be to balance the computational and networking demands of the digital twin application in order to achieve the strict KPIs of the operational digital twins, mainly related to latency and bandwidth. The main goal of this demo is to show how the D6G platform can automate the deployment and efficiently manage the traffic of a real-time end-to-end digital twin system. And for this, we'll show the capabilities of a service and management orchestrator and an infrastructure management layer D6G components, and how they can improve the digital twin system. The demo will be executed at Fivetonic in Madrid, which is one of the two main testbeds of the project, led by UC3M. And now I'm going to present the hardware and the software configuration of the testbed. So this is the hardware setup. So we have a quadruped robot, specifically the Unitree Go1 model, that is going to be mounted with user equipment in order to connect to the radio access network. Then as radio access technology, we will use a Wi-Fi 6 access point. For low latency, this access point goes directly to a programmable switch, and the programmable switch links directly to the Fivetonic Edge data center, where we are going to use a set of servers in order to deploy the digital twin application. Finally, there will also be some additional UIs that will generate the background traffic during the workflow of the demo. On the software side, we have integrated the different components as a microservice-based architecture that runs on two different Kubernetes clusters. So first, we have the SMO layer, which is in charge of the optimal deployment and lifecycle management of the digital twin system. And specifically from the SMO, we'll show the following subcomponents. So first of all, the data lake that will store the container images for the applications. Then the service catalog that will store the service graphs for the network functions and application functions to be deployed on the D6G side. So in the demo, D6G side represents the edge server 1 that is in the 5-tonic data center, along with the underlying infrastructure, so the programmable switch, the access point, and the robot. And finally, the service orchestrator that will manage the request for the deployment of the digital twin service. He will retrieve the service graph from the service catalog and the data lake, and he will send it to the IML component. Then we have the IML, which is in charge of the interactions with the local virtual infrastructure on top of Kubernetes, and the interactions with the programmable switch to perform the traffic management of the application. Finally, we have the per packet value traffic management component. So this component basically tags the packets from the digital twin service with importance values. And based on these values and the queue state in the programmable switch, he uses an active queue management algorithm to ensure quality of service. Then the robotic software is implemented using a robot operating system, and the digital twin is implemented using the open source robot simulator NVIDIA Isaac Sim. So here you can see the application functions that are part of the distributed digital twin applications. So we have the digital twin, which provides the virtual replica of the UC3M robot. Then we have the ROS master, which provides naming and registration for the digital twin service modules. Then the gesture control app as a method of controlling the robot. So for this, we have implemented an application that enables to control the robot using the gestures based on the camera inputs and an AI model that translates these gestures into control commands. Next, we have the SLAM, simultaneous localization and mapping, which provides algorithms to create indoor maps of the environment using the robot sensor data. We have the Go1 base, which provides the interface to interact with the robot drivers using ROS. And finally, we have the ROS driver for the LiDAR and the camera of the robot. The Kubernetes cluster is implemented using the K3s distribution, and the communication between the pods is established through VXLAN. So now I will explain the scenario and the workflow of our demo. So the workflow will start with the deployment of the network functions and the application functions by the SMO with the help of the IML. So this includes the switching capabilities into the programmable switch and the distributed digital twin application that is here in blue. So basically, by doing this, the robot will be able to connect to the access point, and the service can start to operate. So once the service is running, the robot will start sending upstream the joint state, the LiDAR, the odometry, and the camera flows. These traffic flows in green here will go to the data center, and they will start to be consumed by the applications. And from there, we'll start to generate control commands downstream to control the robot. So this means that we'll have a user that is using the digital twin. There is a camera recording him, and he will use his gestures to control the virtual replica. In the moment he controls the virtual replica, this will start generate control commands that are being sent in downstream to move the physical robot. Then, as the physical robot starts to move, we will see it replicated in the virtual world in real time, and at the same time, we'll show how a map of the indoor environment is being created. Next, we'll simulate some background traffic from the UEs into the programmable switch. So this will saturate the network link. and will directly impact the KPIs of the digital twin application. So we will show the performance degradation in the applications. At this moment, the SMO with the IML, they will trigger the traffic management capabilities into the programmable switch in order to protect the important flows of the robot and ensure that it can continue to operate correctly. So in this case, the important traffic flows are the joint states, the LiDAR, and the control commands. This per packet value traffic management component basically consists of modifying the policy of the traffic of the robot traffic, ensuring that it has a guaranteed minimum bandwidth with high priority compared to the simulated traffic. And finally, before concluding the demo, I would like to mention that the Zahir platform has a multi-agent system component, which is based on intelligent agents that are capable of making autonomous decisions in networking. So in this context, the MAS could automatically detect the network congestion in the network link and trigger the traffic management into the programmable switch without the interactions from the SMO and the IML. Okay, so now we'll proceed with the workflow that I just described before.
We will start with the first step, which is the deployment of the service. First, the service orchestrator will receive a request for deploying the digital twin service. It will get the service graph from the service catalog, which is a YAML file, and he will send it to the IML for deployment on the Zahir6G site. In this case, the Zahir6G site is already registered, and the service graph is already uploaded to the service catalog. So here you can see the format of the file. And finally, we use this query to deploy the service. So we specify the name of the service graph and the Zahir6G site ID where the service will be deployed. Then this query returns the ID for the service that has been deployed. Now the service has been deployed and the distributed digital twin application is operational. So here we can see how the user is controlling the robot using the gesture control app. And we also see the virtual model replicated in the virtual world and how a map of the indoor environment is being created in real time. Now we are going to simulate the industrial traffic in the programmable switch in order to saturate the network link. As you can see at the beginning, all the flows have the same policy. In this case, the user ID 8472 correspond to the relevant robot traffic and the other flows correspond to the simulated traffic. As you can see, the robot has some control delays and the digital twin is not replicated in real time. At this moment, we'll trigger the traffic management part, which consists of modifying the policy profile in the programmable switch to protect the relevant robot traffic, which corresponds to the user ID with number 8472, and this will ensure a minimum bandwidth of 2 megabits per second. So now you can see that the robot continues to operate perfectly. The results are displayed on this Grafana dashboard, showing the relevant metrics at the application level with and without the Zahir6G platform. So we can observe that the main affected KPI is the latency.
So as you can see, we can still have the real-time control of the digital twin service, and it is being replicated as expected in the virtual world.